Water is one of the most extensively studied substances on Earth, yet it continues to mystify scientists. Over 70 documented anomalies in water's behavior, ranging from its high surface tension to its expansion when frozen, have prompted researchers to search for answers. For decades, the theoretical framework proposed by Nobel laureate Linus Pauling has been foundational in explaining the behavior of water molecules. However, James McGinn, founder of Solving Tornadoes, argues that Pauling's theory has a critical flaw, which could be key to solving these mysteries. In 1950, Linus Pauling suggested that the polarity of water molecules stems from electronegativity differences between oxygen and hydrogen atoms. In his model, oxygen, being more electronegative, pulls shared electrons closer to itself, creating partial positive and negative charges within the molecule. This explanation has been widely accepted and taught for over 70 years. Yet McGinn challenges this view, arguing that the concept of electronegativity obscures the real cause of water's polarity. Rather than an inherent electronegativity property, McGinn asserts that the true driver of polarity lies in the electromagnetic interactions between the atoms in a water molecule. McGinn's alternative explanation centers on the idea that the polarity in water molecules is due to the direct electromagnetic interactions between the oxygen and hydrogen atoms. The oxygen atom becomes negatively charged, and the hydrogen atoms take on partial positive charges because of the influence of each atom's electromagnetic field on the other. This interaction creates a localized electrical imbalance, a far more concrete and measurable explanation than the abstract concept of electronegativity. Imagine two magnets interacting, not based on inherent abilities to attract or repel, but on their positions and relative strengths. In McGinn's model, the charges within water molecules result from such direct electromagnetic influences, rather than being predetermined by a scale of electronegativity. This shift in understanding has significant implications for water's many unexplained behaviors. McGinn believes the answer lies in how hydrogen bonds affect water molecules. Hydrogen bonds are weak attractions between the slightly positive hydrogen atom in one water molecule and the slightly negative oxygen atom in another. These bonds are crucial to water's properties, but McGinn highlights something even more fundamental. Hydrogen bonds actually reduce the polarity of water molecules. When water molecules form hydrogen bonds, additional electromagnetic gradients are introduced. These additional electromagnetic gradients achieve higher degrees of localized electrical balance, counteracting the imbalance that is the cause of the polarity of the molecules. McGinn claims that each hydrogen bond reduces the polarity of bonded water molecules by 25%. This means that the more hydrogen bonds that form, the less polar the water becomes, which could explain why water behaves differently in bulk than at the molecular level. For instance, when two water molecules form a hydrogen bond, 25% of the polarity in both molecules is neutralized. As more bonds form, the overall polarity decreases, shedding light on why water displays its unique properties, such as its high specific heat capacity or why ice floats on water. One of the most intriguing applications of McGinn's theory is its potential to explain atmospheric vortices, such as tornadoes and hurricanes. In McGinn's model, these phenomena involve a water-based plasma that functions as a conduit, much like plumbing pipes direct water flow. This plasma consists of water droplets that elongate into polymer-like structures, strengthened by increased polarity due to partially broken hydrogen bonds. The spinning nanodroplets, created by wind shear, result in a plasma with amplified surface tension properties, providing it with genuine structural integrity. Rather than relying on ionic forces, this plasma forms through the same hydrogen bonding and polarity reduction principles that govern water, leading to new insights into storm formation and potentially offering breakthroughs in weather science, especially in mitigating severe weather events. McGinn's critique of Pauling's theory is more than just a challenge, it is a call for a paradigm shift in how water is understood and taught. By moving away from the abstract concept of electronegativity and focusing on the tangible electromagnetic interactions between atoms, McGinn's approach simplifies water science, offering clearer insights into its properties. This shift can resolve long-standing anomalies and open new avenues of research in both water science and meteorology. McGinn's revolutionary ideas offer a fresh perspective on water's behavior, from explaining its many anomalies to potentially transforming how we understand severe weather phenomena. By focusing on direct electromagnetic interactions, His approach not only simplifies the teaching of water's properties but also holds the promise of advancing research and inspiring new generations of scientists.